Good afternoon, everyone. This is Celso Batalha, and I'm starting 30 minutes of discussion on the core subject of this week, and we are focusing on terrestrial planets and giant planets. So the week before, we have formation of stars and planets, and one of the main points in formation of stars and planets is that gravity plays an important role in controlling the formation of a star system. So gravity takes gas that happen to be spread over large volume and bring that gas to a point where a star will finally reside. So you have basically gas spread over very large volume, and then if the density of the gas is sufficient, then gravity will bring it in. So gravity will act and be able to overcome several forces, and probably one of the most important forces in the gas, preventing collapse, preventing the contract of this gas, is pressure, gas pressure, basically. So energy that is stored in the gas and preventing that gravity overcome it. So, but if the gravity takes place, then we learn that the final result is going to be, separate those two, is a central star, and in regions away from the center part where the star is going to be residing, the gas falls, but it falls in the direction of a circumstellar disk. So in the process of star formation, two things happen, and one is a central star, and the other process is, which is right here, and the other is the formation of a circumstellar disk of material. Okay, and the circumstellar disk eventually will cool down, and out of the disk material, planets will be formed. Now you're going to have your planets, and then you're going to have your dwarf planets, going to have your asteroids and comets and ices and all kind of things. So if you separate the two regions, like okay, I'm going to have my central region, and in a, not in scale, but in a region closer to the star, and don't forget the star radiates energy, radiates light. In a region close to the star, radiation, and in a less extent ways, the particles the star itself sends out or winds out of its atmosphere, it will act on the gas nearby, so that the planets, the moons, everything we find in a region closer to the star will be different from planets, satellites, and everything else you find in region further out. So we find in the solar system segregation of objects. So objects close to the star in our solar system are called terrestrials. And terrestrial because they resemble our planet Earth. Earth means terra, terrestrial. So which terrestrial worlds do we know of? Well, Mercury, Venus, our planet Earth, Mars, Moon, And why not asteroid? Asteroids are also terrestrials. They are rocky type, and as you see in the slides, they have a tendency of being more consistently rich in metal oxides closer to the star, and as you go towards out to where Mars is, they become less. The content of metal oxides diminish. What am I doing here with my pen? Okay. Now, if you go to regions further out, we find the region of the Jovian planets, or planets who resemble Jupiter, sometimes called Jovians. In some books, they don't call Jovians, but they call giant planets, giant gas planets. I like to call them giant liquid planets, and they are pretty much Jupiter and Saturn. And further out, kind of icy planets, Uranus and Neptune. Okay, and then you have also, of course, the comets, balls of dirty ice that populate this region as well. So let's take a look at this slide, this week's slide. And let's just move on. Just a second. I'm taking a lecture. I will go there. So here the words Mercury, Venus, Earth, Mars, they are all terrestrial objects. And typical question, inner planets in order of increased planetary ranges, so you should get that. This table here gives a nice information, and I would like to call your attention to the density. So the density is the content of what the object is made of. So if you look at Mercury, the density of Mercury is bigger than it is of Venus, and also comparable with that of Earth. But Mars and Moon, they are not as dense as it is. So if you look at Mercury, Venus, and Earth, the overall content of it is bigger than it is Mars and Moon. As we're going to learn, Moon is formed out of a mantle Earth material, which is rocky type, not so much full of iron content. Our planet Earth is primarily controlled by tectonism that helps creating volcanoes, that helps to create earthquakes, hotspots, and erosion is primarily controlled by our hydrological cycle and by the existence of an atmosphere. So an atmosphere brings water with some acidity that acts and destroy rocks, and these weather rocks as water or part of a hydrological cycle or wind bring the sediments to zones of deposition. Eventually lithification will take place and rocks are going to be formed. So our planet Earth, the surface is constantly being resurfaced and redesigned by these forces. As opposed to, for instance, in Moon, most of the landscape in the Moon's surface was formed a long time ago as a result of collision of not only asteroids but comets and material that fell back on the moon after the moon itself was formed. Now Mars has also craters, and in this picture here you can see this design that looks like a mud flow, this mud flow called mud splash, indicating Mars has water that might be frozen below its surface. So I think for this week I put one of the activities was based on a tape, and I already covered most of this material, and I feel that I'm here repeating it. If you would like to discuss, don't hesitate to email me, and then I can go with more details if you wish. Okay. And pretty much that's it. Oh, let me show you this. This is important. Differentiation. Chemical differentiation exists in solar system objects as long as they, once in their lifespan, got completely melted or liquid. If the planet or if the asteroid or if the comet became entirely liquid, differentiation can take place, and that means the heavy elements sink to the core of the planet. So the core of this object, Earth, Venus, Mars, Mercury, and the Moon, the core is heavy, is populated by heavy iron. Okay, and surrounding this heavy iron is, in the case of Earth, is a mantle, is a core that is made of liquid iron. In the case of Venus, apparently is just one core. We don't know if there is a liquid phase or not, but differentiation means the core is richer, is made of heavier atoms than it is in the mantle, and that it is in the crust, and that it is in the atmosphere. The lighter elements stays on top, and the heavy elements stays right in the center, in the core, basically, brought to that place by gravity. Okay. Theories of moon's formation. Most of the indicators point in the direction of moon being the result of a collision of two objects. One is Earth, or proto-Earth, and a Mars-sized protoplanet, and out of the mantle of these two objects the moon itself was formed, or a couple of moons were formed, and later on they merged. The moon exerts an important gravitational pull on us, and we call that tidal forces. And since the Earth rotates on its axis once a day, of course. Oops, I don't know what I did. Sometimes I do something with my pen. There you go. Then, as a result, as Earth rotates on its axis once a day, as this picture here indicates, the the Earth locality, like for instance Africa here, goes through high tides, and then 6 hours later, around 6 hours later, goes again on a high tide situation. High tides exist in the region exactly directly to the moon of few degrees because of rotation, and also in the region further out because gravity pull on that region is less than it is closer. So here's this arrow indicates the gravity force on the planet itself. So here, because the gravity is bigger, water is pull and bulges, and in this part the gravity is less, the water stays behind and bulges as well. So we have two bulging equatorial bulge in two regions as a result of this pull. close to equatorial, not equatorial bulge, but is the water is pulled as a result of the moon, and the moon is not so much far from um, the ecliptic. Well, those are the points I would like to review. And when you do the assignments that I extended because the video was not doing well, you might be able to see it all. Right?